we were looking for MOS capacitor and we started with saying I have one kind of semiconductor and I assume right now it is a P semiconductor, but whatever I am saying for P will be valid for N as well with the polarity change. On this semiconductor I have created an insulating layer. In normal case, if this is silicon, generally this is SiO2. Let us say the thickness of this insulator is Tox. The permittivity of this layer is epsilon ox, where epsilon ox is K ox epsilon 0, and dielectric constant of oxide, silicon dioxide in specific, is 3.9. What is silicon dielectric constant? 11.9. Okay. Sometimes you can use 12 and get solutions faster, but otherwise 11.9. In oxide, the dielectric constant is 3.9. Do you know dielectric constant is related to refractive index? So, dielectric constant of a material is some way proportional to the refractive index. Okay. Like for glass has a refractive index of 1.45, it has some relation with this 3.9. SiO2 is a glass. Okay. So glass has a refractive index of 1.45, whereas dielectric constant 3.9. Something कुछ relation है, क्या है, क्यों है, dipoles कैसे एक दूसरे को optically दिखाते हैं, थोड़ा अलग सोचो. Okay. So the silicon dioxide is dielectric constant of 3.9 and that's epsilon 0 if I multiply, that is epsilon ox by, and the thickness is oxide, Tox. As I keep saying, on the top of this, I have created a metal plate and of course on the bottom everywhere there is a metal plate, and this is called the bulk or substrate which I am grounding. This is called gate and I am applying with reference to substrate a bias of VGS. Okay. And yesterday we discussed that depending on the polarity of VGS, there will be three state of situation in MOS capacitor. If VGS is negative, gate is negative with reference to bulk, then we say holes will start accumulating. If VGS is negative, we say hole starts accumulating, because negative charge in the metal must be compensated or induced charge must be exactly equal to the semiconductor charge, and all other semiconductor is charge neutral. Is that part clear? All other semiconductor part is charge neutral, but you have put extra metal charge, so it must at the surface must appear a positive charge which is due to holes, and these holes are coming from the battery. Is that correct? They are not depleted out of this. These will be provided by the battery. Is that clear? And therefore additional holes can be created. We say this is a case of accumulation. Larger the minus VGS value, larger number of holes will start appearing. If I apply plus voltage, yesterday I said, since I am applying positive charge on the metal with reference to semiconductor, I expect negative charges to appear below the surface of silicon dioxide. The first thing it may happen, that since it was a P and your electric field direction is now downwards, the holes at this position, whichever in this whole P semiconductor, actually move downwards with the field and creating acceptors, which are negatively charged, fixed charge. I mean fixed means they don't move. Negative charges, ionized charges are atomic charges. Therefore they are fixed to the lattice. They don't move. Ions do not move. But do ions never move? Ions do move. If you put large energies, they will leave the band itself and will themselves move. Okay. Otherwise ions normally are stable. This, if I increase positive charge, more acceptors will be opened and therefore depletion layer will enhance, so that the extra charge which you put on the metal should get compensated at the surface below the surface. However, as I increase the depletion layer thickness or width as we call, the electric field across this region also starts increasing, and at some value of positive VGS, it may happen that this depletion layer which you have received by then has sufficient electric field now, large enough I would say. I will say how much, I will say define now. At that time, I figure out that in normal semiconductors, so is in the depletion layer, constantly thermally electrons and holes are generated. And since they are generated, there will be equally recombination. So stability has to be achieved, equilibrium has to be achieved. As hole electrons are generated in the depletion region, and if there is no electric field, by the time they will also recombine to keep that depletion layer as it is. So no additional, because what is depletion layer definition? No charges there. Okay. So as soon as any additional electron hole appear, they will recombine. However, if there is a large electric field, both electrons and holes will now experience a force. Is that correct? Holes will move downwards, electrons opposite to the electric field will move upwards. That means they get separated. Is that point clear? As the electric field is large enough, whole electron pairs get separated before recombination. And as they get separated, of course some recombination may be there, but in general we say that is very small. Holes will come down out of the depletion region to the contact substrate, and electrons cannot go anywhere because there is no place where metal is contacting that. So it just sticks to the surface of SiSiO2. These are negative free electrons. Since you started with P semiconductor, you now see at the surface negative charges, free negative charges appearing for you. So the semiconductor has become at the surface or interface N-type, means invert of what P we started with. And therefore these electron layers are called inversion layers. Now the voltage of VGS at which this inversion can be seen is essentially we define as the word threshold voltage. Threshold means threshold to start inversion, threshold voltage. Is that what clear? Threshold, or some old books they may call it turn on. This was taken from the device MOS transistor where device turns on, okay. But otherwise the voltage, almost every device person will call it as threshold voltage. Is that correct? So there is this threshold voltage is also dependent on the depletion layer charge. Why? Because these are the charges you were making available when the VGS was smaller, and as you start increasing positive VGS, depletion layer charge increased. But at certain value of VGS, you figure out that no more enhancement in depletion layer as much compared to what it can generate from the electron hole generation itself. Okay, that separation at that point we say depletion layer becomes constant, and then we say that any time the charge has to, if you draw a figure, not necessarily very good figure, but if I draw the semiconductor charge versus bias or voltage VGS, let's say a positive, this is for this device. So I figure out initially this charge QS, charge is always defined as coulombs per centimeter square. Please remember this is charge density. You have to always multiply by given area. How much is area here? Can you tell me how much? We have not shown three-dimensional, but the area will be something like this. This is the, this area is this into, this is the area which plate is seeing down. Is that correct? So unless I am giving you the Z dimension, this probably I will be able to tell you always. Okay. So let's say this is length and this is W. So the area is W into L. Is that correct? And since we right now do not want to know how much W it is, so we say it is per unit area. So whatever W is there, it will get multiplied by L, and that per unit area I will use it. So this is per unit area. So initially as I apply VGS, QS starts rising and it is proportional to surface potential, and we said the surface potential we declared yesterday is essentially, depletion layer essentially is twice Ks epsilon naught QNE into psi s. And what is psi s? The potential from VGS 0 to potential of EI bending when the applied bias is applied. The band bending of EI is essentially called surface potential. Is that clear? The EI was flat earlier. As you apply bias, it went down. So how much it went down is called the band bending or called the surface potential. Now we know yesterday, since XD is proportional to psi s and semiconductor charge, essentially we call it bulk charge. Bulk word is used when it is due to depletions. Bulk word is used when the charges are due to depletion. So the bulk charge is how much in this case? If this is your XD, how much, this is your XD, how much is the charge there per unit area? Q in A XD per cc into distance, so per unit area. So this is the bulk charges or charge due to depletion layer. At inversion starting, what did we say? At inversion I said psi s is 2 phi. What is phi f? We said EI minus EF is called the Fermi energy. Okay, EI minus EF is the Fermi energy, and potentially, please remember, all band diagrams, this is energy. So which side? This is increasing energy. So what is the potential direction? Downwards, minus QE is downwards, is that correct? So potential is downwards and energy is increasing upward. This fact has to be understood. Potential is measured from the top to bottom, positive. Upward it goes, it's negative. This nomenclature you must have in mind. So if I say it is 2, why did I say 2 phi f? Anyone? We say EI is bending towards EF because you want hole concentration to go down. Okay, because you are reduced. You can see from here more and more holes going down means depletion layer enhances. So as holes move down, P is equal to Ni e to the power EI minus EF by KT equation, Boltzmann relation says EI must come closer to EF. As EI becomes EF, P is Ni. Okay. Now I further increase VGS, EI further goes down below EF. But if EI is below EF, so it is like telling an electron concentration N is equal to Ni e to the power EF minus EI by KT. So we say at psi s equal to phi f, you are neutral, intrinsic, and any additional change in psi s now you are in inversion. However, at that time the number of electrons available to you are very few. So we defined what is inversion. Okay, the first part therefore, as he is interested to know, till psi s goes from phi f to 2 phi f, close to phi f we say we are in a weak inversion. Weak means very small number of electrons are made available to us. Because the figure says, this we didn't say, the figure says after this, it shows proportion e to the power q psi s by KT. So as you cross this, inversion charge will come from the inversion layer itself, electrons, and you don't need any depletion charge to come. Okay. Now this, at 2 phi f, what is EI minus EF? EI, 2 phi f. First is EI minus EF was 1 phi f, when it touches, you go further, equivalent phi f down means net psi s is now phi f plus phi f, that is 2 phi f. At that time, how much will be electron concentration? Equal to the original hole concentration. N is equal to P now there, old P. Is that correct? Because EI minus EF is phi f, EF minus EI also is phi f. So whatever initial hole concentration is, now electron concentration in inversion. That point we declared as real inversion. That means these many electrons are at least available for me. At that time, psi s is defined as 2 phi f. So the point what Budhraj is saying is this: essentially inversion starts when psi s crosses EI crosses EF. That is inversion set in there. Okay. However, the definition wise, even if that is true, the number wise we say it's too small. So we don't call it inversion, so we call it weak inversion, weak. But at psi is equal to 2 phi f and above, we have large number of electrons available, and we say now it is in inversion. So the definition we say, at inversion psi s is 2 phi f. This is slightly catchy, though it should be only phi f, but we still say it is 2 phi f. The reason is this: somewhere in this region both of them are contributing. Some small change in depletion layer is still seen, roots are at that when it is crossing, so some amount is enhancing. So it is not that free electrons are only coming, slight change is seen here also. So to compensate, we don't want to do theory, we say okay, we will say at this time when this becomes 2 phi f, the depletion layer will reach maximum, and the maximum bulk charge, which then should be this, where xd max is given by this. Is that correct? So 2 phi f, okay, what is phi f in terms of concentration from the Boltzmann relation? Phi is EF minus ER, EI minus EF. So what is phi f in our case? फॉर्मूला अभी बोल रहा हूँ, मुंह से बोल ही रहा हूँ ना, ln Na by Ni, P means Na by Ni. Phi f is positive or negative in this case? Band is bending, downward potential is increasing, so phi f is positive when the P semiconductor is going to be used. In the case of N substrate, inversion will occur which way? The band will bend upward because semiconductor Fermi level is above, so it will go upward to create inversion. You go upward means potential is minus with reference to 0. So in N semiconductor inversion, phi f is negative, and that time what should be the formula I should use? Phi f is minus kT by Q ln Nd by Ni. Sorry. Is that correct? Because bands are bending up for the inversion in N substrate and going downwards in case of P substrate. So the polarity of voltage or potential is opposite. From 0 it goes above, means it is negative, going down means positive. So I can calculate phi f if I am given the doping. Is that correct? If I am given the doping, Na is known, phi f is known, Ks epsilon is always known, so what I can calculate? Xd max. If I can calculate Xd max, you can even substitute if you wish. It can be like this: Q Na Ks epsilon naught, maybe 2 here, 2 maybe you can take out. What is this 2? This 2 and this 2 into Kt by Q ln Na by Ni. Substitute all of it. Okay. This QNA has gone in, so with this QNA it cancels with a root of that. So this QNA, K is epsilon 0, 2 into 2 is 4, so 2 outside. So this is the bulk charge. Is that correct? Copper. This is the bulk charge. It is a function of Na by Ni. Na, how much is doping? Here also Na, but this term is smaller. Why? Logarithmic term. This is directly root of that. So one can always say the bulk charge will increase proportional to doping. Is that correct? Root of that, but proportional to doping. So the bulk charges are higher if the doping in the semiconductor is higher. Is that correct? This is obvious. If you deplete, QNA times means larger, the Na larger is the charge there. There is nothing great about that. Is that clear to you? So this fact has to be understood that larger the substrate concentration I start with, larger will be the bulk charges I will get. Now this much is theory is okay. I am interested in, what is my interest? I just said to start with, I want to know when this inversion starts. What is my interest in this? I want to know at what VGS. Remember, VGS is externally applied voltage. That I can monitor. I apply battery. So I know how much is VGS. Internally, how they divide, I don't know. I only see, I can measure capacitance at best. But I don't know how they divide. So I must now figure out how they really divide. Because I am applying VGS, how much is bias and how much is oxide charge, oxide voltage. So I write an equation. You please note down this, assuming that this is noted down. Maybe I'll rub it off now. Okay. This figure I'll keep it because that will help. So now I say, if I apply VGS, it is divided into oxide voltage plus semiconductor voltage. Is that correct? Semiconductor voltage plus oxide voltage. With this I know everything, because once I know surface potential, I know carriers, I know everything of that. But I don't know what is Vox. So now I start looking into Gauss's law once again. I say, yaar Gauss aadmi itna bada tha, kuch to madad karo. So he gave me a good idea. He said, two things I can think in a Gauss's law. One is, if epsilon S is the permittivity of semiconductor, and let us say electric field in the semiconductor at that surface is ES, this is equal to minus semiconductor. This is Gauss's law's definition. The semiconductor charge density is equal to ES into ES, epsilon S into ES. ES is electric field in the semiconductor at the surface. This is permittivity of silicon. That is equal to this. Is very interesting because now I see, I make another assumption, or rather I know this is correct. I figure out these two materials are different, Si and SiO2 are different, but I assume, and which is not a bad assumption in most cases, D vector is continuous from silicon dioxide to silicon. Continuous means equal. Whatever is D in oxide is same as D in semiconductor. So we say D in semiconductor is D in oxide, but D is epsilon SES is epsilon ox. If D is continuous, across SiO2, then epsilon SES is equal to epsilon ox EOX. What is EOX? The electric field in the oxide. Is that correct? How much is this from Gauss's law? Minus QS. So this is minus QS. Epsilon S is minus QS. So I rewrite this equation, epsilon ox EOX is minus QX. However, what is the electric field in the oxide? Just see that figure. How much? Yeah, very good. The electric field in the oxide is nothing but voltage divided by thickness. Is that okay? Vox by Tox is the field in the oxide. I substitute it here. So I get epsilon ox Vox by Tox is minus QS. But what is this term? Epsilon A by D is capacitance, and if I say per unit area, that is epsilon by D. So this is nothing but oxide capacitance per unit area into Vox is minus QS. Is that okay? epsilon by thickness of oxide insulator is the capacitance per unit area, Is that okay? So if I do that, then the next equation should be Vox is equal to minus Qs by, so आगे आपको semiconductor से जोड़ दिया मैंने उसको. Oxide voltage is now seen as something term in semiconductor, which I know I can always manipulate. If I do so, now this equation I come and substitute here. But this Cox is per unit area. This fact should not be okay. Please look at this expression again. At inversion, what is the value of V? What should be the name of VGS I should give? What is the name I was giving? Threshold voltage. So VGS is a threshold voltage when the inversion sets in. So at inversion, VGS is defined as VT, T capital, okay. This T has to be capital because this sometimes people use at KT by Q, okay. So do not get confused many a times, okay. In some books or some this you may find VT small is KT by Q, so don't confuse with this, okay. So it is, if you are very worried about, you can also put H, if so much is your worry, but generally no one uses H, you only use VTs. This is equal to how much? How much is psi s value at inversion? We defined all the time. What is psi s? 2 phi f. Okay. How much is Vox? Minus Qs by at inversion by Cox. But what is the definition I give? How much is Qs at the inversion? Qs at inversion is nothing but QB. Before the electron concentration is there, we say that charges are only because of the depletion layer. So please remember, but in calculation of QB, I have used strong inversion psi s value. So that slightly not good, but okay, accept it. So that is essentially minus Q Na XD max. Is that correct? Minus Q Na XD max. So if I substitute here 2 phi f plus Q Na XD max by Cox. So Vt is equal to 2 phi f plus Q Na XD max by Cox. Is that kind? What is Cox? Per unit area. Please remember, Q is also per unit area. This also is per unit area. So Q by Cox is a voltage, which is a valid statement. This is per unit area. This is per unit area. So Q by C is still V, as we did otherwise. Yes. NAs are what? वो क्या दिखा रहा है वहां डिप्लीशन पे? माइनस Na ना? तो माइनस. Is that clear? These are negative charges. माइनस क्यू एन ए. यदि डोनर्स होते तो प्लस क्यू एन डी लिखते ना, माइनस है ना वहां पर. वी नेवर हैड सेड एनीथिंग अबाउट एन ए एन डी दैट टाइम ऑल्सो. वी से नेगेटिव चार्ज. We never said what value. Value is minus always because charge is negative. Now this, please look at this term very carefully. If you see this term carefully, whether phi f is positive or negative for a P substrate, always positive. NAs are larger than Ni, so always positive. This anyway taken care with sign, this value is always positive. So this is positive, this is positive. So for a P substrate to create an N inversion layer, Vt is always positive. So for P substrate, Vt is positive to create electron inversion layer. Is that statement clear, Hopkar? To create a electron inversion charge in a p substrate, you will require positive VGS to create inversion charge of negative electrons. Is that clear? Yes. But QM has already taken care, na? QM is positive VGS, therefore only I want minus QS, na? Down. Is that correct? Therefore I want a minus charge, so this is minus, na? Where here I am not saying anything, what charge, I am saying semiconductor charge. What it is, I am now substituting, whether positive or negative, I will correspondingly substitute. Why I want to keep this relation valid? Because for P holes creation, I will use the same expression but change the signs there. Okay. Okay, is that point clear? For P substrate, which carriers I am creating? N kinds. Okay, so these are called MOS capacitor. The inversion का जो भी ये होगा, this is MOS capacitor. Is that correct? Why N? The inversion is of N kind. Without going into details, if I change the substrate, that is I change from P substrate to N substrate, what things will change? For now, you can think, it was an N substrate and I want to create holes, positive charge there. So what should be the polarity at the gate to create positive? Negative. So negative VGS will be required to create positive charge below the surface. Is that correct? What will be the value of 2 phi f if it is an N semiconductor? Negative. What will be the charge QS in semiconductor inversion for P? Let's say for PQV, P is how much? Plus QND XD max plus, is that correct? But this sign has nothing to do with this. This sign came as the from VGS plus kind of expression, VGX is Vox plus IS. So if I substitute this here, this quantity will become plus, minus, and this also is minus. So for creation of whole inversion layer in N substrate, Vt is always negative. Is that clear? So for a PMOS device, so the statement is for NMOS, Vt is positive, or sometimes therefore called Vtn is positive, and for a P device, PMOS, Vtp if you wish, is negative. Minus of minus is what? No, you said it the same, so I only retorted back the way. No. Qs is minus epsilon Es irrespective of what Qs value is. This yes, direction will change. That's it. The electric field in this direction, the electric field will change if the polarity changes. So Qs is Es minus Es epsilon S is valid for either P or N. That has nothing to do with what kind of substrate I create. The Gauss's law does not say which charges. It says Qs is minus epsilon S Es. Is that clear? Independent of polarity of the charge. This is Gauss's law. So now this first minus term appeared because of the Gauss's law. But in the case of P substrate, this itself was minus. In the case of N substrate, that is positive, QND So that sign will become minus. Is that correct? So Vt for a P channel device or PMOS device is always negative. For NMOS devices it is always positive. Now there is an issue. The circuit which I will create in real life does not have only N. I can have only NMOS transistors or only PMOS transistors. But I prefer to use what we call complementary MOS where both P and N together. तो एक का VT माइनस है, एक का VT प्लस है, तो बनाने के लिए अब अलग अलग प्रोसेस करना पड़ेगा, क्योंकि ऊपर वाले को जो P है तो उसका निगेटिव VT के लिए बनाना पड़ेगा, सबस्ट्रेट उसका N होगा, नीचे का सबस्ट्रेट P होगा जिसका VT पॉजिटिव, बट सबस्ट्रेट तो एक ही हो सकता है, सिलिकॉन स्टार्ट विद आइदर P और आइदर N, तो कुछ तो भी एडिशनल प्रोसेस करना पड़ेगी दूसरा ट्रांजिस्टर बनाने के लिए, इसके लिए मास्क बढ़ाने पड़ते जाते हैं। आपको बोला था 24 मास्किंग स्टेप्स आर रिक्वायर्ड टू क्रिएट ए नॉर्मल आईसी in a CMOS. That is why it required, because substrate is one. Now I must create, let's say I start with P substrates, I can create N channels, but to make a P channel I must make some N region in the P and then create device from there. दो मास यहाँ लग गए, ऐसे करते जाएंगे तो एक्स्ट्रा हो जाएगा. Okay, so is that theory is clear that NMOS devices are threshold positive, P channel devices are threshold negative. However, we are still not solved the real situation. The real situation comes from this fact. What were the assumptions made in all that we said? First assumption I made is phi ms is 0. What does that mean? The work function in metal is same as work function in semiconductor. बट ये तो बड़ा अनलाइकली इवेंट है कि वर्क फंक्शन आप दोनों साइड का एक ही हो. ऐसा कर सकते हैं, ऐसा नहीं है, बट लेट्स सी. यस, ओके. सो द फर्स्ट, लेट्स से व्हाट वाज द, सो फार वी हैव डिराइव्ड दिस एक्सप्रेशन बेस्ड ऑन आइडियल सिचुएशन, एंड द सेकंड assumption we made is there are no charges in oxide. This also is charge density. Please remember, unless stated otherwise, it is all per unit areas, because Cox is per unit area, so everything is defined in per unit area, so that Q by C is always V. Okay. So let's see, please, we'll now remove this assumption. Okay. We figured out, this is my MOS, and there are oxide charges present, okay, in the same oxide. Now there are two reasons why this occurs in reality. One is called, maybe A, fixed charge, and the second is called mobile charge. Both are positive, always positive. The charges in oxides are always positive, okay, always, both whether it is fixed or mobile. Let's see first the mobile charge. The mobile means these charges are somewhere here and can move. They are not only placed everywhere but can also move. Under what? Electric field. They will move this side or they may move the other side, okay. These mobile charges are because of what? It could be anything, think of it. You have done a glass, have you any time heard of a glass called Pyrex? What is Pyrex? Borosilicate glass, okay. Then there is a glass which most of this cold drink people use, which is called soda glass, okay. The bottles are made of soda glass, very cheap glass. That contains sodium, okay, soda glass. Now this sodium is mobile in oxide. Sodium is Na2O bond with SiO2 is very weak bond, little bit energy it will break and Na will move. The ions will start moving. These are called mobile. Typically around 100 degrees centigrade and a electric field of few volt per centimeter, tens of volt per centimeter, the ions can move left or right, depends on the polarity. 100 degrees required to give an energy, and to move you need fields. Okay. In MOS transistor both will occur. You will apply electric field and device will get heated. Okay. because of current flowing, I square R will be there. So the mobile ions will move during operation of transistors. Now the problem with the other charge is, so mobile charge is essentially sodium related. तो आप थोड़ा सा बैड सिचुएशन बताते हैं. When we make chips or when we make MOS devices, the place where we make them is ultra clean rooms. Okay, we make all MOS transistors or MOS circuits in ultra clean rooms. What is ultra? Essentially, we define a cleanness of a room by the number of particles per unit area or per unit volume floating per minute or per second. Okay, this room, if I describe this room as in some class, how many particles? So I say 0.5 micron particles will be around 1 trillion per cubic feet floating per minute or per second. I remember, I tell you the number, 1 trillion, 0.5 micron particles, will be larger, will be even fewer, but smallest particle if I use, 0.5 micron particles of trillion numbers, not billions, and about 15. Okay. These many per cubic feet floating here. So this is class trillion clean room. This may be a little better because the air conditioning, closed, nothing much comes in, but still it will be not better than class billion. Okay. We need class clean rooms which is less than class 1. Okay. So the clean room which we built in our annex of E department, that is class 100, or maybe some areas are class 10. So what is class 10 means? 10 particles per cubic feet, but now this 0.5 has been further reduced. It is 0.05 micron particles of 10 numbers per cubic feet floating per second in the room. When I move 1 million particles when I just push my hand. Okay. You can imagine, even my presence in the lab may create dirtiness in this. So in most cases, we wear all kinds of apparels which are like surgeons, you must have seen, all covered up, everything with gloves, everything, which is sterile, which does not stick particles. Okay. And we actually get an air shower before we enter, so all the particles, probably the astronauts you have seen, we actually look like astronauts when we are inside. And the present day for 45 nanometer or lower processes, you need subclass 1. Okay. So you need in thousands of square feet area 1 particle of 0.01. Okay. This is a class of cleanliness. So you need lot of filtering of air, lot of flow of air, everything. And of course, due regards to our female parts, they are not allowed to use any facials. Okay. Sodium is the largest amount in facials. Okay. Okay. So this is to give you some interesting features. So in technology, this is major worry. Okay. However, with the modern technology, this number can be minimized to small value which may not bother you so much. Okay. The fixed charges occurs, please, let me have the complete name. Fixed charges are within first 50 angstroms from the interface. Fixed charges are always very close to, within 50 angstroms, close to the interface. Okay. These charges are also always positive, but they are fixed. What does that mean? They do not move, they remain there. थोड़ा chemistry सोचोगे तो पता लग सकता है. Silicon, on the top of the silicon surface, the bonds are open. जितने सिलिकॉन एटम्स होंगे उसका ऊपर का बॉन्ड तो है नहीं, बिकॉज वो एयर है, उसको बोलते हैं सरफेस स्टेट्स. ओके. नाउ दीज सरफेस स्टेट्स, इफ आई पुट ऑक्साइड, most of these bonds will be satisfied. Okay, but some may not. Okay, so it's called trivalent silicon is left there, which is positive charge. So because of that, I will get positive charges very close to the interface, which is within 50 angstroms, at best 100 angstroms. Is that correct? This positive charge doesn't move. Is that correct? Now let's look at semiconductor. I have not biased it anywhere, Fermi levels are wherever there. However, as soon as you have a positive charge in the oxide, by Gauss's law, there is something else is now happening. The Gauss's law said Qm plus Qox plus Qs is 0. Is that correct? And I have not applied Qm. I have not applied Qm. So Qox is minus Qs. What does that mean? If I put a positive charge at this side of the interface, negative charges must appear across for the field to collect there. Is that correct? This means what has happened, without applying voltage, electrons or negative charge started appearing in semiconductor. So band कैसे bend होना शुरू होंगे P के लिए? नीचे आना शुरू हो जाएंगे, डिप्लीशन शुरू हो जाएगा. और यदि ये बहुत ज्यादा चार्ज है Qox, so what it will do? The band bending will be so much that EI may cross the EF itself. So क्या हो जाएगा? Inversion may come in. So at zero bias, I see inversion sets in. So VT कितना हो गया? Minus हो गया. Is that clear? So if the charges are too high, the two positive term in VT, 2 phi f and QNA XD max, may actually be small enough compared to this Qox by Cox, which is minus, therefore VT may become negative. So मेरा एक बड़ा वरी आ गया कि यदि ये ऑक्साइड चार्ज को कंट्रोल नहीं किया तो मेरा VT तो क्या था, पॉजिटिव बनाना था ना इन चैनल के लिए, और वो कैसा बना, नेगेटिव हो गया. And that I don't like, because that means at zero bias transistor will start conducting, as we say later, so it's called depletion transistors. It's not turned off, it is always on, हमेशा के लिए. Unless I apply negative potential, I cannot turn it off. Is that clear? This is my worry. So I must control my Qox. So if I use this, I can show you, थोड़ा मैथ्स आपको quickly बताते हैं. So Qm is minus Qox plus Qs. Since Qox is fixed, either mobile or this, let's say number is fixed. This is varying with voltage. As Qm varies, this varies. But this does not vary with that. Is that clear to you? This is fixed. इसको theory में हम लोग क्या बोलते हैं? If I vary one quantity and the other quantity varies plus something is constant, इसको क्या बोलते हैं? Offset. So this is like an AC variation, DC offset. Okay. So we say since anyway it's not a function of voltage, so I call it Qs dash. Okay. So whatever variation of voltage it will show variation with this, because this is constant. Is that correct? dq by dv in the dqs by dv. So any change here is same change here. So then if I declare Qm is minus this, so वो जो relation था VGS is 2 phi f minus Qs dash by Cox हो जाएगा अभी. तो पहला रिलेशन निकाला है उसमें Qs के जगह Qs dash लगा दो. Okay. This will be then plus 2 phi f minus plus, which is QNA XD max by Cox minus Qox by Cox. So at zero bias itself band bending is possible. Is that correct? Even at zero bias, this term is forcing band to bend down. Is that clear? But from where we all measure voltages? In ideal case, when bands were flat. Is that correct? So we say, I will have to apply this much additional opposite voltage to make that band जो ऐसे थे, उसको वापस लाने के लिए जो voltage मुझे लगा, उसको बोलते हैं flat band voltage. So what is flat band voltage? This voltage will be required in opposite sense now to make bands ऐसे थे, उसको फिर से ऐसा करने के लिए जो bias लगाना पड़ता है, उसको बोलते हैं flat band voltage. Is that clear to you? So which is minus Qox by Cox को उल्टा करने के लिए we'll have to as if उल्टा करना पड़ेगा, तब bands flat होते हैं. This is one reason. Now mobile charge, of course, right now we'll see later, but this creates more problem. Why it creates more problem? Because right now our assumption in Poisson's equation is charges which are closed here will be exactly seen here. But charge which is seen here has a very small effect because of the distance I have on this side. Is that correct? By Poisson's equation. So which means charges away from the interface will not influence strongly. Okay. But since mobile charges keep moving, depends on the polarity it sees, so how many will be here additionally, I have no idea at a given time. So what it will vary all the time? Vt. So as the device is being operated, its Vt is varying. Because of the mobile charges are moving, some may come to the interface, some may move from the interface. At that time, the Vt's are not constant. And why I am worried about Vt not constant? Because that means the current which is Vgs minus Vt will see later. If Vt varies, I don't know how much current I will get. So at different temperature, different fields, I may get different current. So during the process working itself, the chip may show you different speeds or different powers. Okay. This we don't want. Okay. So we must see that mobile charges are 0. 0 of course is not possible any time. Infinitesimally small equivalent to saying or this term इस QX में जो particularly Q mobile term है Q by Cox should be smaller. Is that correct? Q by Cox should be smaller compared to the other quantities. If that happens, they do not influence. Is that correct? They do, but smaller than the other, so we damn care about that. ये प्रोसेसिंग का सबसे बड़ा चैलेंज था 1970s में. क्या प्रॉब्लम था? We could neither control QX, either fixed or mobile. So n channel डिवाइस कभी बना ही नहीं पाए हम लोग. क्यों नहीं बना पाए? Because उसका Vt माइनस कितना रहेगा ये भी हमको पता नहीं था. Is that clear? So we said, if I use same terms for PMOS device, can you tell me what will happen to a PMOS device then? Pt for a PMOS device is minus 2 phi f minus Qox by Cox and minus QND XD max by Cox. All quantities are negative. तो ठीक है -3 वोल्ट आता है Vt तो आने दो, मैं 10 वोल्ट का पावर सप्लाई लगा देता हूं. ओके, पॉजिटिव का निगेटिव हो गया तो मुझे नहीं क्या पावर सप्लाई लगाना, पर अभी -3 का -4 होता है तो मैं 10 वोल्ट लगाता हूं ना, Vgs माइनस Vt फिर भी बढ़ा दूंगा. तो इनिशियली in 1970s all chips were only PMOS chips. The first Intel 4004 was a PMOS process. Same was 4K. First SRAM memory was also from the PMOS. In 1978 onwards, when we could control these fixed charges drastically lower, then NMOS started. Is that correct? So A78 onwards, all chips became NMOS. Can you tell me why NMOS will be superior than PMOS? Mobility, because the drift current, the number of electrons and number of holes being equal, even if it is equal, the current will be mobility related, smaller or larger in N or P. Is that clear? So same voltage लगा और कम करंट लो, ऐसा किसने बोला है? तो N यूज किया, बट देन सबको लगा कि नहीं यार